Chuck, can I ask a quick question before we get started?
Of course.
So I was wondering, so in our stats class, we're doing a lot of like linear and logistic regression, and I'm finding myself writing out coefficients. And I was wondering if there's a way to do coefficients in line in the way you could like calculate a mean. Is there a way to do that so I don't have to keep updating when I update the regression?
Yeah, absolutely. Here, I'll show you. Okay, so let's say we've got some kind of example linear model. I've got something like so if I pull like a summary on this LM object, right, I've got two coefficients. I've got one on weight, one on horsepower. Well, if I want to get quick access to the coefficients themselves, there's a function called coef_lm that will give you a vector of those actual coefficients. And then from that, I could easily say something like coef_lm WT and get just the weight one or something like that, right? And so that's accessing it by name. If I want to get the standard errors and stuff too, I would instead want to work off the summary object and say something like summary coefficients. That will give me a matrix of the coefficients. And then I could do something like, for instance, if I wanted the standard errors, that would give me the vector of the standard errors of the coefficients. I could just get their estimates like that. Or I could, for instance, pull the entire row for a single variable like weight here, and that would give its estimate standard error t-value, p-value. If I wanted to zone in and get just weights standard error, subset both, and that will give me its standard error. So you can access these things like they're, you know, they're basically just a named matrix or something in R. The ones straight out of coef are a vector, but here you can just access it like that. So it kind of depends what you want to do, but all of them are subsettable like any other R object. So you can just dig into them and pull out what you want.
Great. One more quick question related. If we're doing like writing out an equation in LaTeX, will it, when we're doing it in line, will it pick that up? Will it pick up the coefficients, or would I just be able, I would have to do that part in the text? Did that make sense?
You could do it inside the actual, so it depends whether you're, no, actually you should be able to do it in the LaTeX. So if you've got some LaTeX equation, yeah, you can insert, like I could do something like, you know, what would be a good example? It'd just be like doing like y equals, I guess you wouldn't need to use /beta, but here you could use like R coef, let's grab times weight. I'm just gonna do this WT here, something like that. Should work in the LaTeX, where what it's going to do is it's going to pull out this number here, and then the rest of it's just going to be text inside. That should work in a markdown document.
Okay.
Yeah, I've done that kind of mixing and matching for a lot of things to produce equations and things like that. Yeah.
Great. Thank you.
Any other kind of random questions before I get started? Also, a quick question. When you folks are talking, does my microphone reverb your audio? Usually? Okay. That's funny because every other application I found out apparently does it, but it doesn't in Zoom. So they've got some kind of nice audio compensation going on. Good on Zoom. Many other things suck about it, but that's nice. Okay. Okay. So I will go ahead and get started here. Looks like we got 32 people in. That's pretty good numbers. Okay. Yeah, so today is loops. Okay, so if somebody didn't know any better in what they're doing, this is a common thing I see people do who are relatively new to R, if you wanted to find, say, the means of every variable in the Swiss data set we used back in homework 1, they might get it by typing in a line of code for each column in the data set, right? They might be like, okay, I want to get the mean of every variable, so I get the mean of fertility, agriculture, examination, so on and so forth. I assign them all to mean 1, 2, 3, 4, whatever, and then I bind them together into a single vector to get those means, right? Well, if you look at something like this, there are actually a lot of errors inside this code that I'm showing. And the thing about this is that you'll see some of them pretty much immediately because they kind of break a pattern, but some of them are more subtle, right? So here I'm like, mean 1 is the mean of fertility. Oh, that's great. Mean 2 is the mean of agriculture. That looks like it might be right. Here I've said the mean 3 is the mean of Swiss examination, which R thinks is a single object and is going to kick an error. Here I've said mean 4 is the mean, again, of Swiss fertility. This is the kind of error that won't kick any error in R. It's not like going to pop up red text. You're just going to accidentally assign the same mean to 2 different means here, and you might never know that you've done that, right? This is the more insidious type of error. Here I've said mean 5 is the mean of Swiss Catholic, and then here I accidentally said mean 5 again and did the mean of infant mortality, overriding it. Then when I tried to stick them all together, I did mean 1, mean 2, forgot a comma here, which will kick an error, and then here I said man 6 instead, right? There's a million different typos in here, and the more stuff that you type, especially similar looking things, the easier it is to insert typos like this, or even worse, insert mistakes that won't kick an error like mean 4 and mean 1, which will accidentally be the same values, right? The other sort of issue with this, other than making typos, is that can you imagine how upsetting this would be if you had 200 columns instead of 6 columns in the data set, right? It doesn't scale well. A linear scaling like this really sucks if you have larger and larger data sets. So we don't want to do things this way. Okay. Good repetition is making the computer do repetitive tasks for you, because computers are, by their nature, far better at repetitive tasks than we are. So what you're going to learn today are what I call general solutions for repetitive tasks. And then you're going to learn better ones, but which are usually somewhat more specific next week. Better ones also being writing functions to accomplish things. Loops, what we're going to learn today, are sort of a blunt instrument. So you can do any repetitive task that exists using a loop. So if you learn them, you might kind of get in that situation where you have a hammer and everything looks like a nail. You really don't want to be solving all your problems with loops, though, for a number of reasons, which will become readily apparent over the next hour or so. But know that any problem can be solved with a loop. And in some programming languages, loops are the only way to solve some of these problems. There's some programming languages that don't allow you to operate over entire vectors at once, which is something we're going to talk about in a bit, and so you'd have to do everything with loops. A nice thing about learning loops, as complicated as they are and as bulky as they are in R, is if you go to any other programming language, every programming language basically has loops in it. And some programming languages is the main way to work with things. You need to know loops at least a little bit to perform tasks sort of in general programming, but I wait till week 6 so that you learn a lot of better ways to do tasks before I introduce something that you could use for everything, but which will make your life much harder. Okay, so I'm not going to explain exactly what's going on in this code because we're going to walk through simpler examples and build up to it. But the gist of this is that I want to get the means of all these columns in the Swiss data set. So I create an empty vector here that I'm going to store those means in it. And then I use something called a loop, which we're going to talk about in a while. What this loop does is it basically calculates the mean for each variable in the Swiss data set one at a time, assigning them to the appropriate element of this Swiss means object. I can then print it out at the end, and what I get are the means of all of the variables in the Swiss data set. So this iterated over each element of the Swiss data set, that being columns in it, producing a single number for each column and spitting it out, okay? So the nice thing about some kind of code like this is if I wrote this in the Swiss data set instead had 500 columns, I wouldn't have to change a single character of this code. It would just print out a 500 length vector with all of the means of the Swiss data set. This is the nice thing about writing code that's good for like repetition. It doesn't matter how big something is, it just scales. It has instead of having like linear scaling, like writing them line by line, or even exponential scaling, it just doesn't scale at all, right? It's just speed you lose, okay? Okay, so The idea behind most of this stuff today and even next week is going to be the DRY principle. The DRY principle is don't repeat yourself, right? Computers are much better at doing things over and over again than we are, okay? Writing code to repeat tasks for us rather than us doing those manually reduces the most common human coding mistakes, right? If you're writing line after line after line of the same stuff, eventually you're going to make a mistake. Doing repetitive stuff sucks. The whole point of programming is to make the computer do the stuff that sucks and you do the stuff that's somewhat more interesting. Okay. Another thing is that it will substantially reduce the time and effort involved in processing large volumes of data. If you're not writing a line for every column in the data set, it's going to be a lot faster for something big. Okay. And well-written repetitive code tends to be very fast. Some of the code we're going to learn today, and especially like next week, is incredibly fast for most operations. And lastly, and this is a big one, compact code is much easier to read and it's much easier to troubleshoot. It's common for people who are newer to programming and things to try to impress people by saying something like, oh, I wrote 5,000 lines of code on this thing. If somebody wrote 5,000 lines of code to accomplish something, you probably should not listen to that person's advice about writing code. They wrote way too much code to do something unless it is something incredibly complicated, okay? The thing about actual software development is most people who write real software write very small amounts of it per day, right? We're talking sometimes people will be writing 10, 20, 30 lines of code over an entire day, right? But what they're doing is they're doing it elegantly in a way other people in the organization themselves can read in the future, and that operates quickly, reliably, all that, right? Your own scripts to try and sort of follow this, and that you want to write less code. Don't be obsessive about it. It's very easy to prematurely sort of optimize your code and try and squeeze out into as much small a space as you can. You don't need to do that, but at the same time, if you find yourself writing a single script file and you have like 500 plus lines of code in it, you should either be breaking it up into multiple tasks because it's probably doing multiple things in one script, or you're doing something really clunky that could be done in a more efficient and more reliable way. Okay. So the agenda for today is sort of fundamental programming stuff. So way back in the first week, I said that this class teaches intermediate data analysis and visualization and basic or introduction to programming. This is one of the first lectures that's actually basic programming rather than being something specific to data manipulation or analysis. Okay, so what we're going to cover today are for and while loops for programming. These are general methods found in basically every programming language. And then we're going to cover vectorization to avoid writing loops, okay? Next week, we're going to talk about writing your own functions and then looping based on your own functions and doing vectorized stuff based on functions you write yourself. The real power in a language like R is writing your own functions to perform these repetitive tasks for you. We're going to get into that next week. Okay, so what is a loop? This is one of those rare cases when for a technical thing, the explanation in Wikipedia is actually one of the most concise and well-written ones I've seen. So I'm going to be straight bad and read directly from Wikipedia on what a loop is. A loop is a sequence of statements which is specified once, but which may be carried out several times in succession. The code inside the loop is obeyed a specified number of times, or once for each of a collection of items, or until some condition is met, or indefinitely. Okay? So loops, as it turns out, are basically the backbone of every piece of software and every software run device that exists in your life, okay? So your cell phone, under the hood, your cell phone, and see how it just lit up when I picked it up? There was actually a loop sitting there on my phone waiting to detect changes in light or even motion to turn the screen on. But there is a loop automating that process in the background. Likewise, there are sort of loops that do things like consistently ping the cell phone tower to check what your connection is. Loops to do all sorts of things like that. There's a loop that monitors your battery power by periodically pinging the battery or checking its voltage and things like that, right? All of these things are actually loops under the hood. Okay? It's some repetitive task done over and over and over and over again. Nothing is truly continuous in a computer. Instead, it's something that's done very, very, very often and has the appearance of being done continually. Every time that thing is done is one time through a loop. Okay? So when I say loops are general, I mean it's a loop. Go up deep down your computer, eventually it's all loops. Everything is a loop. So if you can master loops and things, you can actually perform basically any task a computer is capable of performing. Okay, so first thing I want to talk about is for loops. So for loops are, at least in data manipulation analysis, the most general kind of loop. They're found in pretty much every Turing-complete programming language I can think of. I don't know of any languages that you can code iterative tasks in that don't have a for loop. They're really common. So the idea for a for loop is, for each of these values, which you'll provide, in order, do this thing. So conceptually, you will provide some set of values. This set of values could be something like a whole bunch of numbers, like the numbers 1 through 10, but it could also be columns in a data frame or something like that. So given that set of values, you will set an index variable equal to whatever the first value in that is. If we're iterating through the numbers 1 through 10, you would set this index to 1. Then we'll do some set of things which depend on that value often. Then once we're done doing those things, we check to see if there is a next value in this set of values. If there is, we update our index to that value and repeat number 2. Then we continually do this until we run out of variables in our index. Once that happens, we exit the loop and stop repeating our activities, right? The idea here is that we are looping through this set of values to repeat an action. Visually, a loop looks something like this, okay? So given some set of values, we will set, I'm going to say here the variable we're going to set is I. We're going to set I to the first value of these set of values. Then we enter this loop. In the loop, we will run code using I. Maybe our loop is something as simple as print a value of I. Then, once it's done doing that, it will check and see if there's more values of I. If we haven't run through all of them, we're going to say, yep, there's more values. I will be updated to the next value in that set of values, and then we'll do the code again. And if there are 10,000 values, we're going to go through this circle 10,000 times, right? Once we run out of values, it's going to say, are there more values? Nope, we stop. That is the entire essence of a for loop, okay? That's all it does. Okay, so we're going to put these into action. Here is a very simple example of a for loop in R. We're going to say for I in 1 to 10. To decode this, the set of values that we're going to run our loop over is 1:10. This is the integers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? The I here is saying that inside this loop, I want to replace the variable that is the object I with first the number 1, then the number 2, then 3, then 4, then 5, then 6, then 7, then 8, then 9, then 10. So this function for just specifies I want for a given value in order in the numbers 1 through 10, do whatever is inside my squiggly brackets. So the for loop says we specify sort of the parameters of the for loop, and then everything inside the squiggly brackets afterwards, everything inside that will happen once for each value up here. So if I run this loop that says for I in 1 to 10, print I squared, it runs, it squares 1 and gives me 1. Then it prints and squares 2 and gives me 4, 9, 16, 25, 36, so on, all the way to 100. All this loop is doing is assigning a new value to I and running the print command the exact same way we could do it manually in the console. You'll see it runs the print command 10 times. That's why the output says element 1 every time. It's running the print command 10 times. It hasn't created a single object with 10 elements. It's actually just printed 10 times to the console. Okay? Pretty straightforward. Questions about that so far? Okay. I start with something very simple and accelerate continually. So we will see. Okay. So to put these side by side, a loop that says for I in 1 to 3, print I squared. This is the exact same loop, but I'm just saying 1 to 3. It produces 1, 4, and 9. This is exactly identical to if I said assign 1 to I, print I squared, assign 2 to I, print I squared, assign 3 to I, and print I squared, right? The output is identical because these statements are doing exactly the same thing. There is no difference to R, basically, between these two statements. All this is doing is assigning values to I, running something, and then overriding I with a new value. Okay. So we call whatever happens inside the loop for one particular value in iteration. This is a term I have used throughout the term because it's sort of baked into my brain forever. An iteration is just what happens inside that loop once for each value. Iterating over indices like 1 through n, that is 1:10, is really common. N might be the length of a vector, the number of rows or columns in a matrix or data frame, or it might be the length of a list. These are all things we might iterate over. So here's a question over here. Do you have to use print everything, or could you do object assigned to that object? No, you cannot assign the result of the for loop directly to an object like that. The issue there is the for loop has actually produced 10 objects over the course of its operation. If you wanted to get the output of this loop here and save each one of these, we would instead need to assign this value to the first element of a vector, this value to the second element, and this value to a third element. This is called allocation, and we're going to get there. And you'll see it becomes a little bit more complicated if you want to save the output of loops, because each time it runs, it produces another object. And as we know from R, we can't have a single command in R produce multiple objects. So instead, we would have to run those commands and store them on the fly as the iterations go. This is the complicated thing about loops, which will throw you for a loop, so to speak. Oh God, I hate myself now. So we'll get there. Okay. Yeah. Okay. So common notation for loops. I will be an object that holds the current value inside the loop. This is really commonly done. So I did it before where I said for I in 1 to 10. If loops are nested, that is, you have a loop inside a loop, maybe inside another loop, it's common that people will use I, J, and K as you get deeper and deeper into multiple nested loops. Okay. Now, this sounds kind of odd and abstract, but if you spend any amount of time looking at like math notation for statistics, you'll actually find that loop notation, commonly used loop notation, is identical to common mathematical operations. So for instance, if you take the summation operator in math, so this says sum I equals 1, that is begin with I equaling 1, sum until I equals n. Right? This is a loop summing up all the values, beginning at the first value and going to the nth value. Okay? This means anytime you see some mathematical operator, like the sum operator, the product sum, or something like that, if you see it, you can write a loop that will perform the exact same task and generate the same result as the math. Okay? So this is something, you never know, maybe you want to manually write a statistical routine from the formula. You can totally do it with loops. Okay. In R, it's better to do it with vectorized notation, but you could totally write a loop to do it. Here's a question here. Can you create a loop that names the objects as they are created? Yes, but it's a little bit weird and it's highly discouraged to have a loop creating objects. It's far better in R to create an object ahead of time and use the loop to assign values within that object. There's a principle of good programming called no side effects that R tries to obey, and a side effect is spontaneously generating objects inside functions. It's usually not good to do unless you do explicit assignment, but you can do basically whatever you want in a loop. If you can run the code to do it in your console, you can do it in a loop. Okay. So the thing in loops, though, is that these symbols like I, J, and K, there's nothing special about them. They're not reserved objects like true and false in R. They are just normal objects, meaning instead of iterating over I, you can iterate over any object name you want to create, right? So instead of iterating over I, if I'm going over rows in a data frame, I will iterate over an object I create called row. If I iterate over columns, I will call it call or column, right? So you can have your loop iterate over something, whatever name you want to use, whatever makes the most sense to you. It's flexible. It's just an object like anything else. We just conventionally use I, J, and K because we don't tend to use I, J, and K for anything else. They're not like, there's no functions in R named lowercase I, J, or K. There is an uppercase I that you do not want to overwrite. So just keep that in mind. Okay. So we don't have to iterate over just numbers in a loop either. We could iterate over a character vector in R. Here, I'm going to say the object sum letters is equal to letters 4 through 6. So this is just going to be, if we remember, letters is a vector in R that contains the 26 lowercase letters of the English alphabet. I can get the 4 through 6 letters, which are D, E, and F. So sum letters is literally D, E, and F as a vector. I could say for I in sum letters print I. So what it's going to do is it's going to go and print the first element of some letters, then the second element, then the third element, right? So this here is a length 3 vector. If I say for I in this, it just runs through every element of this vector, and for each element of it does whatever is inside the loop, okay? So I can iterate over character vector 2. Something to note, after this loop is done running, whatever value I was assigned in the last iteration of the loop, it stays that way. If I call on I after the loop is run, it remains F, because F was the third value of some letters, the last value, and that's what I was the last time the loop ran, right? I is just an object like anything else, and all the loop is doing is assigning values to it, one at a time. Once it finishes the loop, I stays in the environment. Okay. Which sometimes might be useful to you if you want to know, for instance, how many iterations something had to run. You've got it at the end and you could check what its number is or something. Okay. So a nice shortcut sometimes for running loops is sequence along. If you do sequence along X, it will create an integer vector that starts at 1 and goes to the length of X. So here, if X was a length 10 character vector, sequence along X would produce the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? It's just a shortcut for this. Okay, so when you want to loop over something that isn't numeric, but you need a numeric index of where you're at the loop, sequence along can be useful, right? So you could say, for instance, for A in the sequence along some letters. If we remember, some letters is a length 3 vector of D, E, and F. So sequence along some letters here is the numbers 1, 2, and 3. I could then say, I would like to print, paste together letter A, that's the current iteration, colon space, some letters subset A. So in the first iteration, A is 1. So it's going to say letter 1, colon space, D, because some letters first element is D, right? So we get letter 1 is D, letter 2 is E, letter 3 is F. At the end, if I run that A here, you can say A finished off being 3 and not the letter F because I used sequence along. I see a question here. Two questions, rather. One, does that make things funny if you use the term row instead of I? Does that make things funny if you use the term row instead of I? I'm not sure what you mean exactly on there. You could use whatever you want. I use row if I'm iterating over rows, column over columns, data frame if I'm iterating over data frames. I just use descriptive stuff. You just wouldn't want to, by the value continuing to be assigned to row. No, that would be fine. I mean, assuming row isn't a function you're using in your data frame or something, you wouldn't want to iterate over something like data.frame and have every iteration of your loop right over the function data frame or something, but it's fine with like row, if that makes sense. Next one, is there a way to clear it at the end? Yeah, you could just do RMA, for instance here. RMA would remove the A object from the environment. RM is delete or remove. Another one, do we need to initialize A to hold the value 1, or does R do this for us? So this is an interesting thing about R and loops, unlike many programming languages, is it creates this A object when the loop starts running. We don't have to initialize it ahead of time. And if you attempt to initialize it ahead of time, it will actually overwrite that value when the loop starts, okay? So usually any loop any for loop like this, if you want it to start at a particular value, you want to make that value you want to start at the first value of this thing that you're looping in, right? Okay. Yeah, it's a little bit different. People who come to me with programming backgrounds in lower level languages are used to initializing everything with a value. R kind of does some of that stuff for you under the assumption that you know what you're doing, which even with me, is kind of a gross assumption. Okay, so this be similar to expression a function. Similar to the expression. I'm not sure what you mean by that expression, a assign function. I mean, this is pretty similar in that the loop is essentially running assign to a each value of this one at a time, if that's what you mean. Yeah. So it's basically, yeah, exactly. That's what it's doing under the hood, is it's going to assign the first value of this to a, run the stuff inside, and then do that assignment and run it again. So it really is just doing that assignment operator. Yeah. Okay. So pre-allocation. Oh, what does paste do again? So I will show you. So if I go here, let's say that what I want to do is, here's an example. So paste here, paste just takes whatever text is given to it. So this is a length 1 vector of text. This is a length 1 vector of text. If I paste them together, it makes it a single vector of text. Okay. Paste, though, is a vectorized thing. So if I say something like the number, I don't have to do C there. If I do, let's go 1, 2, 3, 4, 5. I paste that together. The way paste works is that paste will take this vector and make a single vector out of them, but the number of elements it has will be equal to the number of elements in the longer of these two things. So if I paste together the numbers 1, 2, 3, 4, 5 and just the number here, I get the number 1, the number 2, the number 3, the number 4. It repeats it. So paste is used to stitch like two elements or more elements of text together into one element, but it will also operate over entire vectors if you want to use it that way. Okay. I'm just using it kind of like this, stitching one thing together at a time. Okay. Hopefully that didn't induce more confusion. Okay. So pre-allocation. So usually in a for loop, you're not just printing output like I've been showing before, and it's sort of like what I mentioned before. You might want to store results from calculations during each iteration somewhere. Okay. So to do that, you need to figure out what it is you want to store and pre-allocate an object of the right size as a placeholder. And by pre-allocate, we mean we're going to create some object like a vector that just contains NAs or zeros, and then each iteration of the loop, it's going to overwrite one element of that thing, storing the thing we're interested in. Okay. The thing is, though, is that you have to pre-allocate, that is, create this object ahead of time so the loop has a place to put that element. Okay. So some examples of things you might want to pre-allocate based on what you're going to store in the loop, right? So in the loop, if for every iteration it produces one numeric value per iteration, that is a single element, you might want to create, say, a numeric vector of length equal to the number of iterations. If you have a loop that's going to run 10 times, and for each iteration it's going to get like the mean of a variable, you need 10 elements, that is a length 10 vector, to store those means. Okay. If you were going to generate a single character value per iteration, you'd want a character vector of length equal to the number of iterations. If you're going to do true-false values, you'd want a logical vector to store it in. If you had, for instance, a loop that generates a whole numeric vector for each iteration, you're going to want to store those values in a matrix, right? Because each vector needs a whole row or a whole column to go in. Okay, so we'd say here, matrix, I'd fill it with NAs. You might have the number of rows equal the number of iterations. So each iteration fills in a row, and the number of columns equal to the length of the vectors produced by the loop, right? So the first iteration, it would fill in the first row. The second iteration, it fills in the second row, and so on. For more complicated objects, you might just want to use a list, because if you remember, a list could store anything in each of its elements. So if you don't know what your loop is going to produce, or if you know that it's going to produce something weirdly shaped, right? You can do it with a list, and then each one of those elements will just be the result of an iteration, and you can figure out what to do with them later. Okay. So here's an example. I'm going to run a loop that's going to run for 10 iterations. So here I'm actually just going to say the number of iterations is going to be 10. My output, that is what I'm going to save the result of my loop to, is going to be a numeric vector of length 10. Iterations is 10. numeric 10 says create a length 10 numeric vector. Okay. Then I'm going to say for I in 1 to 10, so 1 to the number of iterations, run this thing below. And see here, I'm going to assign to output i's location. So this says for iteration 1, assign something to output's first element. For iteration 2, its second element, up till we get to its 10th element, just assigns as it goes. Then we're just going to do some math, which is a series, a mathematical series I forget the name of. It's just I minus 1 squared plus I minus 2 squared. Okay. I run this loop and I display the output. And the output now stores the result of the first iteration, second iteration, third, fourth, fifth, sixth, seventh, blah, 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 right? So this is what the pre-allocation is all about. We assign an empty vector to output so that we have these subsettable locations to put our results in. If I didn't create this output object here, this thing couldn't be subset. I couldn't assign anything to it and the loop wouldn't run. Okay. Yeah, we just need something empty to store it. Does that make sense? Any questions about that? This is usually where brains start to break slightly. They will break unevenly. Some people will break earlier, but all will break by the end, probably. Okay. Mine definitely did. I did not take intuitively to loops, so this is not something I expect people to intuitively take to. Okay, especially as we get later in this one. So again, if we don't know how many iterations there will be, we make it a list. No. So even if you make it with a list, you probably want to know how many iterations there are going to be if you're going to be storing your output. If you're in a situation where you have no idea how long something is going to run, and you need to store the results from every single one of them, you are in a problem called growing an object. And growing objects, that is adding elements to them, is the slowest operation imaginable in R. So the problem in R is if you want to add one element to an object, R has to copy the entire object and produce a new one with that added element. And that becomes prohibitively slow. So normally it's a good idea to figure out how many iterations something is going to go, or pre-allocate an enormous object and assign values to it until it's done and then remove the unused slots. Okay. There are other cases where you can get around this through other clever ways, but normally you don't want to be growing objects by adding elements because it's really slow. Next one. Do we have to pre-allocate the length of vectors, or we can use something like append function within loop to dynamically modify the length vectors? Yeah, that's the same question there. Appending things in R is tragically slow. This is actually all belief in the world about R being a slow programming language has actually come from this appending problem. R is actually basically exactly the same speed as Python, but R has slow at appending because it doesn't modify in place, it replaces objects. This makes it quite slow for this. So the R workaround is essentially proper pre-allocation. Okay. There are some other things you can do, but we don't want to get into them. Okay. Okay, so set names is a convenience function I want to mention here for pre-allocating objects, okay? So set names allows you to create the object you want to pre-allocate to and give it names in the same operation, okay? So let's say what I want to do is I want to create a vector that looks like this down here. I want to create a vector where it's going to be an empty numeric vector. As some trivia, if you create an empty numeric vector, it's filled with zeros, not NAs. That's just our convention. It's filled with zeros. Good to know. If I want to create an empty numeric vector, but each iteration has names like this, iteration A, B, C, D, E, there's two things I could do. So I'm first going to create the names I want to use, once again using the paste function. Here I say, I want to create names which are equal to paste 0, iteration, and then letters 1 through 5. So R will recycle iteration here to be the same length as letters 1 through 5, producing iteration A, B, C, D, and E. So this gives me some names to work with. I then create a numeric vector of length 5 called a vector, and I could assign names to a vector, names to use assigned to names. This would give me this vector down here. If I wanted to do it all in one line, because I'm obsessive about the line count in my code, I could instead use set names. This works like this. Set names, the object I want to set names for is this vector numeric 5. The names I want to assign to it are these, and I assign the result of all of that to a vector. So what this does is it will create the a vector object and assign the names to it in one operation. This saves me one line of code, but it's a nice trick to know about because every once in a while you'll think of some situation where you actually can't do this operation up here because it's programmatically difficult, but you can do this one down here. You might be like, how could that ever be the situation? It's happened to me about 100 times. So it will crop up sometimes, especially when you're programming like functions and things. Okay, yeah, good to know about. So now we're going to get into the weeds here. We are going to do a challenging extended example of using loops to show sort of the power of these like iterative operations, right? So this is an example using linear regression. It's perfectly fine to not be familiar with linear regression. The idea here is that we're just going to fit some really basic statistical models to some fake data. But the main thing is that we want to run multiple models without having to run each one manually. And then we want to test each of these models later without having to test them all like manually one at a time. Okay, so the premise here, let's imagine that we have some data and we want to try fitting several regression models to it. In this example, I think I'm only going to fit 4 models, but if you're in some kind of more data science-y type thing, maybe we're trying to fit 1,000 models to some data set, right? You don't want to be doing them one at a time. You want to be able to iterate over models. Okay. What we want to do is we want to store the result of fitting each regression as the elements of a list so that we can compare these regression output, right? So the output of a linear regression, as I've mentioned in past lectures, is a large list object. So the only thing sensibly we can store its results as are elements of a list. If you wanted to convert it into something else, it could be elements of a data frame or something. Okay. So to do this consistently, we're going to do a loop. The nice thing about doing this with a loop would be if we have 2 models, we write the code one way. If we have 200 models, we can use the same code. It will scale regardless of how many models we have. So the code I'm going to show is for 4 models, and then later I'm going to show cross-validation with it. But if you had 1,000 models, you wouldn't have to change a letter of the code. It would just work. Okay. So after we do that, we're going to try something even more advanced that involves loops within loops called cross-validation, which is a way to estimate the true predictive accuracy of a model by kind of simulating out-of-sample prediction. This is a, again, rather complicated thing that you might encounter in some later statistics classes. I do it as an example for 2 reasons. One, it's a nice example of a practical application of 2 loops, one inside another. And also, if you ever want to do cross-validation manually later, perhaps you're asked to do it in a class, you can steal my code. It's a nice operation to be able to do. Okay, and this is something that I teach also for UW-Tacoma's Masters in Science and Business Analytics. I know for certain my cross-validation code is in use in multiple business projects because they're like, oh, it works pretty well. Like, it's simple. Okay, so first thing I want to do is I want to simulate some data that has sort of a known distribution so I know for sure which model should fit the best on it. So it doesn't matter exactly what's going on here. This is basically me just generating a data set with 300 observations, a specific mean and standard deviation for the main predictor, and then some relationship between X and Y, and some normal randomly distributed error in here, okay? There is an aside, and one reason I like to keep this slide in here is there was a scandal in political science in about 2014 when a graduate student, got a paper in Science, the highest journal in the land, after falsifying his survey data. And it was discovered he was falsifying his survey data because all he did was crudely generate fake values in the survey data and literally add noise using R's rnorm function to generate randomly normal noise. So in the future, it's important to know if you're ever going to falsify data that nothing is ever perfectly normally distributed in its error. Okay, that is not a thing. And people like me will smell that from a mile away. Okay, so as soon as those raw data came out, somebody immediately saw it. It's literally impossible. It was actually due to it being a, what you call it, it's like a feeling thermometer or whatever. It's like rate 0 to 100 how you feel about this group. Nobody fills in randomly distributed around 50. People just put 50, right? Or 0 or 100 or 20. Nobody does, oh, I feel 48 about this. And it still got into science. Anyway, don't fake your data with our norm. Be an adult about faking your data. Or, don't fake things, You do you. Okay. So if I plot these simulated data here, they look something like this, right? It's a simple ggplot of it. My data, they have an x variable on the x-axis, a y on the y-axis, and they've got some sort of noisy parabolic shape like this, right? If you know anything about regression models, you'd probably know that fitting a straight line through this is going to have a pretty garbage fit, okay? So the real question, though, is what kind of bendy line is going to fit best through here? If you saw the way I generated the data, you probably know, but we're still going to test a bunch of different regression models. Yeah, there is occasionally some weird person who would think about it a lot and then be like, yeah, I do feel a 48 on that. It is a rare person, though, not literally everyone. Hilarious, though. So our candidate regression models for this that we're going to fit are going to be an intercept-only model. This says just fit a horizontal line through all the data. That is, I think the best way to predict these data is with the mean of all the y values. So x doesn't even come into the equation. We're going to fit a standard linear model. This draws a line that fits to the y values as a linear function of x. So this means we have some intercept and then we have some slope based on x. So x times some value, fixed value, there should be a straight line. We're going to fit a quadratic model. The quadratic model just makes it a parabolic curve, which, as you might expect, is probably going to fit pretty good because I generated this data using a quadratic. And then we're going to get complicated and fit a cubic model, which will make this sort of an S sign. So it's going to curve up and then down and up, or the other way around. Okay, so we're going to fit these 3 different models. Okay, so if we want to fit, well, 4 different models rather. If we want to fit these models and run a loop over them, what we need to do first is, well, first thing I want to do is I want to generate a named character vector that's going to store the formulas to fit these models. So I'm going to create an object just called models. In it is going to be a vector like this. So if you remember, in a vector, you could just give it the values you want, but you can also do name value pairs in the vector. So this says, I want to create the first element of this vector is named intercept only, but the actual element is y tilde 1. The thing on the right side here is a formula. This is the formula for fitting an intercept only model in R. Y depends on a constant. We're going to name it intercept only. We're going to name y tilde x linear. We're going to name y tilde x plus I x squared quadratic. And then we're going to do this cubic formula here and name it cubic, okay? The nice thing about this structure is if I subset models, so if I say, you know what I'm going to do here just to make sure I can run this because inevitably problems will arise, I'm going to run this directly in my R as we go. Okay, so generate my data. Generate my models, and I will demonstrate why this models vector is structured this way. So I create this models object here. Cool thing about it is, so if I run it, we can see models is like y tilde 1 intercept only. If I wanted to say pull out the formula for the linear model, I can just say models linear, and it spits out that linear formula. So this means I can do subsetting on the models object and get the formula I want, which is how we're going to run these models by iterating over this vector here in a minute. Okay, so the next thing that I want to do now that I have a vector of the models is I want to create an empty list to store the models that I'm actually going to run. So I say, let's create this fitted LMs object. It's going to be a vector of type list. Its length is going to be equal to the length of models. Well, its length of models because we're going to fit 4 models, so I want it to be length 4. Okay. I'm going to give it names. The names are going to be equal to the names of the models. okay? This is going to generate a list that looks like this. Its first element is named intercept only. Its second is linear, quadratic, and cubic. The nice thing about this is it means my models object and my fitted LMs objects all have the same names. So I could subset the model and where the model's results are going to be stored using the same like subsetting element, right? If I say I want to do models linear, I get the formula. If I say fitted LMs linear, double subsetting for a list, I will get the place I want to store the result of the linear model. And then if we know how looping works, remember, we're going to take an element like for I in the models, but I is going to be replaced with the name of the models or whatever, meaning we could replace this with like I and this with I, because they're the same thing, and inside the loop iterate over both the model we want to run and the place we want to store it, which is what we're going to do. Okay. So what we want to do is we want to loop over the vector of models, fit each one of the models, and store it in that appropriate slot in the fitted LMs object. Okay. So first thing we want to do here is that fitted LMs object, or not the fitted LMs, but the models object contains these formulas that look like this. We want to make sure R recognizes those not as text, but as an actual formula. We're going to need to use the formula function in R that will make sure to convert that character string to a model. In some situations, you can just give R the raw text quoted like that, but in LM, it usually doesn't like it. Instead, we need to have it convert it to a formula, okay? So to give you an idea of the difference between that, we see here if I do models linear, you see how it's quoted like that? If I run, oh, geez, that just broke everything. How the hell did I do that? Okay. See the difference between these? This vector here is quoted in text, but the actual formula needs to be this unquoted formula object. That's all the formula function does, is convert it into something that looks like that. Okay, so we do that. So here is our loop that we're going to run. We're going to say for mod, and mod of course is just going to be like I, it's an object we create for this loop. For mod in names of models. So this means inside the loop for each iteration, mod will be replaced one at a time with each of the names of the models. So for the first iteration, mod is going to be the text intercept only. For the second iteration, it's going to be the text linear, then cubic, and then quadratic, and then cubic. Okay, so we can walk through this first iteration. This says, take fitted LMs, subset it to intercept only. So this over here is the intercept only element of fitted LMs. To that, we want to assign the results of an LM function with a formula. The formula is the models object subset to intercept only, meaning this thing right here is y tilde 1. In quotes, this makes it just y tilde 1 as an object. And then the data is going to be our simulated data. So this mod in names mods does double duty. It does two things. It subsets to the appropriate element of our list object, and it subsets to the appropriate formula from our models object. Okay? If I take this and run it, what we end up with is this big list object where each element of the list is the output from a linear regression. Intercept only, which has just an intercept. Linear model, which has a coefficient for x. Quadratic, which has one for x and x squared. And cubic, which has one for x squared and x cubed. Okay? So, does that make sense, the magic going on making that work? Do we have questions about that? Does it actually make sense after many years of giving this lecture and trying to make it make sense? Do we have questions?
What would you do if you wanted to get other values that typically, like if you just do L, M, Y, tilde, X, data, whatever, it would pop out like an R squared and an F. How would you get all of those things?
We could now extract them from the list objects themselves. So for instance, we have fitted LMs here like this, right? Fitted LMs is just this object down here. If I wanted to get like, I could say, give me the fitted values of the linear model. And that would be the fitted values for all 300 observations of the linear model. So I can subset down into this object. If I wanted the fitted values from all 4 models separately, I would honestly use an lapply, which is a function I haven't introduced yet. We're going to see how to work with these larger objects over the course of today and next week. Next one. Can you set bounds on the values produced by the model? For instance, if we know I cannot realistically be bigger than 1. Oh, so like bounds on the coefficient estimates? Is that what you're asking? Or because on the yes, the coefficient, you can, but it's a little awkward to establish boundaries. You actually have to, technically, I would think what you'd need to do is swap to a generalized linear model, something based on optimization under the hood, and then give it constraints on its parameter values in Optim. You absolutely can. You can't with an LM because unlike basically every other statistical operation anyone can ever do, LM has a unique algebraic solution that can be solved analytically. And so putting constraints on it doesn't usually make too much sense. It's like kind of a weird thing putting a boundary on the matrix space. You can do it for GLMs though, quite trivially. No. Not that I know anything about that. Okay, so yeah, so all we've done here basically is we've done the exact same operation I could do in 4 lines like this. I'm going to write it out so you can see what I'm doing. I basically just said that's intercept only. This is linear. This is linear, and then the same thing for quadratic and cubic. That is all the loop is doing, is replacing mod with the appropriate text from names models. The names of the models, again, is just intercept only, linear, quadratic, and cubic. So you could do this manually and see what's going on. Does that make any more sense for a couple people who've been shaking their heads? No. A little bit better? I would toy with it, and do please ask me questions as we're going, because it is going to get more complicated rather than less complicated. Okay. So that's all that's happening, right? We're doing a little bit of substitution. We're making the computer replace mod with something else, but otherwise the code is exactly what it would look like if we ran it in our console. Okay. The loop doesn't do any magic. It's just doing a repetitive operation, writing this once instead of writing it 4 times. Later, I'm going to show you how in R, unlike many languages, we can do this same repetitive operation like this without writing any of this text up here and here, using something called apply functions. So if the thing that messes with your brain is the setting mod and going names models and stuff, we can actually get rid of that stuff later on. Okay. So next thing. We want to plot the results from these fitted models. So we want to see graphically how well these models do with our simulated data. So what I want to do is I want to get predicted Y values from each X value in our data for each one of the models. Okay, so what I'm going to do is I'm going to pre-allocate somewhere to store our predicted data, kind of. I'm going to say we're going to create a new data frame called predicted data. It's just equal to my original simulated data frame. Okay, and then I'm going to iterate over the exact same thing. I say for mod in names models, that is mod is going to be intercept only, then linear, then quadratic, and then cubic. What I want to do is I want to assign to predicted data a column named mod, because predicted data is a data frame. If you subset to something named, it will be a column. I want to assign the results of the predict function, take the fitted linear regression object for mod. So for instance, fitted LMs intercept only, and use the predicted data. What this generates right here is just the fitted values for the model. Okay, I'm going to run this. So here's a question. If we look at predicted data, let's get head on it so I don't display the whole thing. So we see that there is an X column and a Y column because it's the same as sim data. So what am I doing here when I say assign to predicted data mod? Does anyone know what I'm doing here? Oh, I guess I wrote text in there. So we do know what I'm doing because there's a comment directly above it. I'm creating a new column. What I'm actually doing here is I'm telling the loop to loop over mod and model. So it's going to go predicted data, something named intercept only, and it's going to assign to that the result of this prediction function. If you assign to a named element of a data frame and that named element doesn't exist, it will create a new column in the data frame. So if I do predicted data, sim data, run this, what it has done is created a new column named intercept only, a new column named linear, a new column named quadratic, and a new column called cubic. So these are essentially, given this X value and the model intercept only, this is the predicted value of Y. Given the linear model, this is the predicted value of Y. Given the quadratic, this is the predicted value of Y, and the cubic, right? These are, each column is predicted values of Y given a value of X. This is all this loop has done, is run through and generated a bunch of columns. Does that make sense? If not, please ask me questions. If anything you can think of would clarify. Okay, this is me just getting fitted values for 4 columns at once instead of doing it one line at a time, which here takes about the same amount of work to do 4 in a row in a loop as it would to do them manually, but if we had 200 of these, it would be a huge pain. So what is the Y column? The Y column is the actual original Y value I used to fit the model. So if we remember that, for instance, linear is a linear regression of Y tilde X, this Y is the actual Y value used to fit the model. Okay. Y is the original data, basically, what X and Y are. Okay, so I can look at those predicted values. I just saw them in the console before. This is exactly what it is. New columns for intercept only, linear, quadratic, and cubic. The thing is, though, if I want to plot these results on a ggplot, I want intercept only, linear, quadratic, and cubic. I want them to all be in one column. I want them to all be in a prediction column, and I want another column that says which model the prediction belongs to. So what I want to do is I want to pivot my data longer so they're in long format instead of in wide format. Okay? So what I do here is I say, I'm going to load up tidyr from week 5. I'm going to say, I want to create tidy predicted data. This is going to be equal to our original predicted data on the last slide. I want to pivot longer the 3rd through 6th column. Thus, I want to pivot the 3rd through 6th column. I want to create a names column called model that's going to store the old column names. I want to create a values column named prediction that stores the old values in those columns. I then turn model into a factor with levels equal to the names of models. This is just to put the model variable in the order that we ran them in. This is purely for aesthetics. If I get ahead on this, we see we now have, for every value of X and Y, it's repeated 4 times. We have a model, intercept only, linear, quadratic, and cubic, and the prediction associated with that X and Y. This is just a long repeated observation format of the previous slide's data. But this now is ready to go into ggplot because I could say, take all these predictions, make a line plot of them grouped by model. Okay, because I don't want to plot 4 separate columns. I want to plot one column and group it on something. Then what I do is I do a quick ggplot of this. There's one tricky thing in here I do. I actually do a geom point plot of the original data instead of the tidy predicted data because it actually has 4 X and Y like redundant points for if I did a point plot. So I'm basically sticking these 2 data frames together. The important thing is this. These are the predicted lines for all the different models we just fit. So we can see our intercept-only model. It's a horizontal line through a parabolic curve of dots. So yeah, it looks like it fits pretty badly. Our linear model, the green one, doesn't really fit much better. Yeah, it arcs a little bit up here on the right, but it's still a pretty crappy model. But then we run into sort of an issue. It's hard to tell which one of these other two models fits best. The quadratic model and the cubic model are almost identical, right? The only difference here is it looks like the quadratic model pulls in a little tighter to the far left and right ones, where the cubic model seems to maybe fit some of these other ones around here a little bit better. But basically, I look at the two of these things and I'm like, these look basically indistinguishable, right? And if I had more data points, it wouldn't get easier for me to tell them apart. Instead, it would probably be just as hard or harder. So it's hard to adjudicate graphically here. And if I did common fit statistics, most of the common fit statistics wouldn't do a good job adjudicating between these models either. Okay, so one approach we could take to figuring out which one of these models we might want to use is cross-validation, okay? Cross-validation is a really widely used method to estimate how well models make predictions on unseen data. That is, we are going to look at how the model does if it fits the model with one set of data, leaving out some chunk of it, and then uses those coefficients to predict the stuff we left out, okay? This is cross-validation, okay? So the procedure to do cross-validation is you will split your data into K folds is the terminology. These are just chunks of data. If you do something called 10-fold cross-validation, it means you slice your data frame up into 10 equally sized sets of rows, okay? That's all it is. A fold is some set of your data, some selection of rows. Then what we're gonna do is for each fold, I through K, so if we've got 10 folds, we're gonna do this 10 times. We will fit a model to all of the data except the data in that one fold. If we have 10 folds, we're going to fit a model using 90% of the data, okay? Then we will make our predictions for the omitted data. That is, we'll fit our model on 90% of the data, but then in that predict function, we're going to put in the 10% we left out and see how good of a job the model does with its predictions, okay? Then we will calculate some measure of accuracy. I'm do mostly statistics, basic statistics, so I do mean squared error. Some people like mean absolute deviation and things like that, but mean squared error is common. Mean squared error is just the difference between the actual Y values and your prediction squared, and then you take all those values and take their mean, okay? So it's the average error, average squared error in the model. Okay. Well, models that fit well or do a good job in prediction will tend to have low mean squared error. Models that are too simple will make bad predictions, and models that are too complicated will make bad predictions. So in either way, they tend to have high mean squared error. So the nice thing about this cross-validation procedure is it will give poor results for either too simple or too complex models, right? Whereas there's many types of ways of assessing model fit that will always sort of say that an overly complicated model is good. Cross-validation will punish overly complicated models. Okay, so visually speaking, this is what this cross-validation is going to do, okay? For the first iteration of the model, we're going to leave out the fold one rows. We are going to run a model, say, of Y on X using folds 2, 3, 4, and 5. We are going to extract the estimates from this model and predict using them. We're going to take the fold one rows, put them in that predict function, and predict predictions for fold one. So the model is fit with these rows. The prediction is done with the data we left out, and the prediction gets assigned over here in some pre-allocated space for these fold one rows. That's iteration one. We just run through all the iterations. So at the end, we're now leaving out fold 5, predicting fold 5, and we filled in each of these pre-allocated spots with predictions for their corresponding rows. Okay? Does that make sense? Ish. We're going to basically do this. If it's 5 folds, we're just going to predict 5 times. We say, fit this model, predict, stick it here. then here, then here, then here, then here. So if you've got something that you want to do identically many times that you iterate over, loops are a good way to do it. So we're going to walk through the code to do this. Okay. So the first thing we want to do, right, is we need to pre-allocate that thing over here on the right side to stuff things into, stuff our predictions into. Okay. So what we want to do is we want to pre-allocate some object for that, and we want to split our data up into 10 distinct folds to do our 10-fold cross-validation. Okay. So one way that I can generate folds is to randomly assign the numbers 1 through 10 to every row in the data set. So here's a question here. Each fold is mutually exclusive. There's no replacement. Exactly correct. We want to make it so every fold is the exact same size, and each row is randomly assigned to a different fold. So we're essentially going to take the numbers 1 through 10, repeated over and over again 300 times, and randomly assign those to our rows. 300 times because there's 300 rows. So the code to do this, I say, we're going to say k is equal to 10. So k is the number of folds we're going to do. If you want to do more folds on some data set, change this number and the code will do it for you. I'm going to say CV predictions is just going to be equal to our original simulated data, meaning we're just going to add on some stuff to it. CV predictions, I want to assign folds to every row in our data. To do that, I do exactly what you say there in chat. I want them to be mutually exclusive with no replacement. So I say, I want to randomly sample from something. What I'm going to randomly sample from is I want to repeat the numbers 1 through 10, 1 through k, right? Length out is equal to the number of rows in my data. So this is going to repeat 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 30 times, generate 1 through 10 until we get 300 rows, basically. But then I want to randomly sample from this. Replacement equals false. So this means it's going to assign randomly each of those numbers in this vector to this fold over here until it runs out, which means, and I'll show you, well, actually, it kind of shows it here. Fold, for instance, this randomly assigned the first row to fold 9, the second to fold 5, the third to fold 8, 3, 1, 6. This is the first time I've ever run this code and not gotten the same number multiple times in the first 10. Fun facts. Okay. I also do one tricky thing here. So what I want to do is I want to assign the predictions for each model to their own column. So I've abused a little trick in data frames. I say CV predictions, subset, comma, names models, and then I assign NA to it. So you've seen before that I assign to a data frame some named element that doesn't exist, it will create a column. Well, it turns out if you use single bracket subsetting and assign to a named vector of columns, it will create all the columns that don't exist. So names models here is a vector of intercept only, linear, quadratic, and cubic. If I assign NA to this, it just generates 4 columns filled with NAs. It's a little assignment trick. I could have done each of them individually, but I like to write something compact and teach you a trick at the same time. So basically this CV predictions data frame now has the original X and Y values, a new fold column that's going to tell us how to allocate or not allocate these rows to different models, and then 4 columns that we're going to fill in predicted values for. Okay, I'm going to take this, run them. Okay, looks good to me. Yeah, see, this is what I normally expect is it gets like 10, 10, 10, 3 10 assignment folds in the first 6. That's what usual random data looks like, is randomly you get weird clumping and people are always like, that looks non-random. If something looks like immediately non-random to you, that is often an indication it is in fact random. Things that look good and random are usually a lie somebody's constructed to make look like random data. Okay, so we're going to do something complicated here, because what we want to do is we want to loop over every single one of these models to do our cross-validation. But then within each one of those models, we want to loop over each one of the folds. So we're going to do something called a nested loop. That is, I have taken one loop and stuffed it into another loop. This is a very common programming operation to have loops inside of loops inside of loops. In R, it's really common to do your best to avoid doing this, but it's nice to demonstrate how this works. So the idea here is we're going to loop over each model. Within each of those models, we will loop over each fold and make predictions. So I'm going to walk through how this happens on the very first iteration of the loop, okay? So the first loop is for mod in the names of the models. Well, this is the exact same start to the loop we've used for every other one of these regression loops, right? Mod is going to be replaced with intercept only, linear, quadratic, and cubic. Okay, where we're going weird is we've got another loop in here. So for now, let's imagine mod is just intercept only, the first iteration, okay? Then what we're going to say is for k in 1 to capital K. Remember, capital K is just the number 10. So this is literally for k in 1 to 10. So for the first iteration, k is the number 1. So first iteration, mod is intercept only, k is 10. What we're going to do is we're going to create an object called fold rows. Fold rows is going to be the CV predictions fold equals k. So what is CV predictions fold equals k going to produce? Is anybody right? Well, I guess I've annotated this, so now we know. This is going to set a whole bunch of trues and falses. This thing is going to be true whenever the variable in CV predictions, the variable fold, is equal to our current fold. So this means this thing, fold rows, will be true anytime that row is fold equals 1. Then for every other row in the data that doesn't have fold equals 1, this thing will be a false. We can use trues and falses to subset our data, which is what I'm going to use them for. Then I say we're going to run a temporary model. This is a model that runs inside the loop. We're just going to extract some stuff from it and overwrite it every time the loop runs. We're going to run the same model we ran before, linear regression. The formula is equal to models, the name mod. So this formula right here is y tilde 1, because that is the model's intercept only model. Okay, same model we fit before. The difference here is this. Instead of saying the data equal our simulated data, I said they equal CV predictions, not fold rows. Exclamation point takes all the trues and turns them to falses, and it takes all the falses and turns them to true. If you subset something by trues and falses, it keeps the trues and discards the falses. So the result of this is this data frame is the CV predictions data frame with all of the fold rows removed, right? This is what we wanted to do in our procedure. Take the CV prediction data, drop the 30 rows in that fold, and fit a model to it. It's the same model as before, but it's only fit on 270 observations. We've dropped 30 of them out. Then what I want to do is I want to save to the CV predictions the rows that are in our fold. We're going to predict values for the fold rows for the intercept only model. Okay, so if we remember back in our image here, we are predicting in fold 1, we're predicting for fold 1. So that's what we're doing. We're going to run this model and save the predictions from it to the fold rows. Okay. Okay. So in the model column, so what this says is go to the 30 rows that are fold 1, go to the column that is the intercept only model, and assign to those values the result of prediction using the model we created. So we've run this model here on 270 observations, but the data we're going to use in our prediction is CV predictions fold rows. So it's the same code as this, but without the exclamation point. So this data set here is the 30 observations in that fold. So the prediction is generated using this model, but the data is from the fold, okay? So this is complicated, and I'm aware of that. And it's okay to be looking at this and being like, you're doing some weird shit here, Chuck. It's fine. But know that this is sort of the power of the loop. We're sequentially going over 4 different models doing 10 different predictions for each model, and we're doing all of it in this tiny little block of code, of which almost half of it is comments explaining what I'm doing. I'm going to run it. It runs instantaneously. I'll get ahead on that. The result is going to be that we get predictions now for each value of x and y. We get an intercept-only prediction, linear prediction, quadratic prediction, and cubic prediction. But this prediction here for fold 10 was done using a model that left out these rows here for 10. So the model was fit without these rows, but then after that model was fit, it predicted y using the x values here in the actual model. That's all that's happening here. It's very similar to what we did without the CV, except we're swapping what data is being used to predict things. Okay? So the next thing I could do here is, what do we actually want from this? We don't want those predictions even. We don't care about them too much. We care about something we can calculate from them, which is the mean squared error. So what I'm going to do is use a loop to compute the mean squared error of those predictions. And this squared error, so the squared error is just the difference between the real values and the predictions squared. And the mean squared error is the mean of all those squared errors, okay? So what I'm going to do is I'm going to make a new vector called CVMSE to store the mean squared errors. I'm going to say, let's set the names of this numeric length model. Says I want a vector of length equal to the number of models I have. I got 4 models, so I'm going to get 4 mean squared errors. I want the names of that vector to be the names of the models. So I'll get the mean squared error of the intercept only and so on models. Then I'm going to loop over the exact same thing again. Every example here has been looping over model in names of models. There's no reason to complicate it. This is our workhorse and it can just do it for us every single time. What I'm going to do is, for each model, I'm going to predict the squared error, which is just going to be all of the CV predictions y values, subtract from that the predictions of the given model. So this says take the actual y value, and in the first iteration, go get the CV predictions intercept only column, take the difference of those things, that produces the error, square them produces the squared error, okay? This ends up being a vector of length 300 because there's 300 data points in our data, so there's 300 different errors. Then I just take the mean of that squared error and I assign it to CVMSE, intercept only, linear, quadratic, or cubic for each iteration. Okay? I display it, and this is the mean squared error for the intercept only model, the linear model, the quadratic model, and the cubic model. Now, you don't have to know the metrics of this or anything. The only thing that matters for the mean squared error is whichever one is lowest is the best one by our CV. So you look at this, and now we have an independent way to determine that the quadratic model appears to have fit these data better than any of the other models. And if you actually saw the data generating process I used with the simulated data, 0.955 is real impressive because I inserted exactly 1 point of random error into the model. So this thing's doing about 0.45 better than theoretically is possible. So it goes. That thing would approach 1 if I did this with a larger data set. Okay, so that is a complicated example of doing big nested operations. It's very complicated, and I don't expect this to be something where you're going to be like, oh, I totally understood everything done. But the nice thing about this example is it's not some bullshit example of something that no one would ever do. Instead, this is actual in-operation CV code you could put into a paper and do cross-validation with. So if you're interested in it, take this code, adapt it, use it, ask questions on it. But this kind of shows what powerfully could be done. If instead our data set was 10 million observations, we had 1,000 models, you could take this code, modify nothing, and just press button and get results, and you'd be good to go, okay? This is the powerful thing about this iterative code. So I know it's complicated, but I resisted removing this and putting in a simpler example because this is an actual real life good example. And I try to only include things I actually use. This is one of the only times I actually use loops, like nested loops anyway. Okay, So now that you've gone through that burdensome topic, let's go to things that are less oppressive. So that right there is, in my opinion, the pinnacle of difficult things for the entire term. It is now all downhill from here. Okay. So the next thing I want to talk about is conditional flow. So you've seen the function if-else in R. If-else is for doing logical checks on a vector and assigning values. It is not to be confused with if and else. Those are different things. So if and else are for doing single logical statements on a single value and not a vector, and then conditionally executing a set of actions. You often will use if and else inside of loops or inside of functions to do things, often to do things differently when different numbers are given. Here's an example using a loop. I say for I in 1 to 10. So we're going to iterate through the numbers 1 through 10. I say if I modulo 2 equals 0. Modulo, or the modulus operator here, takes the number on the left of it, divides it by this, and returns its remainder. Okay? So this is the way of checking if a number is even. If you divide a number by 2 and its remainder is 0, it is an even number. You could also use the is.even function, but I'm old school and I always use modulo. So if I is divisible evenly by 2, print the number I is even. Okay? If this statement here returns a true, it runs the code inside. If this statement does not return a true, it will keep going. It says, okay, if this is false, else, check this statement. So if I is divisible by 3, print the number I is divisible by 3. If this statement here is also false, it will say else, and notice there's no if statement here. If there's no if statement, it's just going to run the thing after else. Then the number is not divisible by 2 or 3. Okay? One of the very few tricky things about formatting in R that's actually R is particular about is the else statement. Else must come on the same line as the closing squiggly bracket of the if statement. So you see I've got this closing squiggly here. The else must go there if you want to use an else statement. It's one of the rare times R cares where you put stuff, but it does in this case. Okay. If I run this loop, this is what it prints, right? For number 1, it's not divisible by 2 or 3. 2 is even. 3 is divisible by 3. 4 is even. 5 is not divisible by 2 or 3, right? So what it's done is for each one of these numbers, it's worked its way through these conditional statements. It's like a little decision tree. It runs through them all, and it assigns things to the appropriate code to run. Okay? This is called conditional flow, and it's how everything in every computer does everything you ask it to do. Okay? Everything you've ever told a computer to do, there's basically a statement in there being like, well, if they do this, return this thing. And then somewhere in there is a, if I do something I truly did not expect you to do, print an error. That's how everything in your computer works, and it's how every argument in R works too. Okay. So a nice thing to use if statements for is handling special cases. Maybe you have a big, glorious loop and it works for 9,999 of your 10,000 cases, and then it gets to that 10,000th case and explodes and you lose all your results. You could use an if statement to catch the things that normally would break your code. That is, to catch problematic cases. It's also a good way to make your loop say ignore cases. Maybe you have it looping over subsets of data and you want it to catch when there's not enough observations to run your model, or there's no, for instance, maybe you run over and it checks to make sure that a categorical variable has multiple levels, because if it's a constant, the model can't run. Weird special cases like that, okay? Another thing if statements are useful for is generating error messages in functions or in loops. If it finds something unexpected, you can say, if you see this thing, print warning, right? Every function in R that prints one of those errors to console has an if statement that generates that error, saying, oh, if I get something unexpected, yell at them. Every time you've ever been yelled at, somebody programmed R to yell at you in that specific way. So there is someone out there to be upset about errors like, you cannot do that to an atomic vector, which doesn't make any sense to anyone. Someone wrote that, and an if statement generated it. Okay, so Here's some common example of using a loop for something else that might be more useful to people. One thing I've used loops for a lot, and I don't necessarily use them for anymore, I'll show you faster methods next week. You could use a loop to load many files in at once. Let's say you have a directory filled with Excel files. For this example, I'm only going to use 10 Excel files, but it's not uncommon, at least in my experience, to have like 150 Excel files. I had a project I was on recently that I had, nearly 1 million CSV files that I had to iterate over. So sometimes you get a lot of files, right? Anyway, you might want to load them all and not manually type in all 1 million file names. Okay, so let's say we've got this folder of CSV files. There's a function in R to get the file names in a folder. It's called list.files. If I say list all the files in the example data directory, when I ran this, these were the names of all the files in that directory. If you download my class as a zip file, this folder with all the CSV files will come with it, okay? So file list equals list files this, and we have all these file names. Okay, next thing is let's populate an empty list of the same length as our file list, right? If we're gonna read in a bunch of CSV files, the output of a CSV file like that's gonna be a data frame. We can store a data frame as each element of a list. So I say data list is going to be a vector of type list, length equal to the number of files. We got 10 files, we need 10 slots in a list. To get nice object names, I use the stringer package to cut all of the .csvs off the end. This just says remove from file list the .csvs you find. So now the names for data list are going to be like this, no .csvs. Okay? I then assign those names to the list. Could have done it all with set names, but did it one step at a time. Then what I'm going to do is I'm going to run a loop that will read in each data file, write it to the appropriate element of data list. So I load up the reader library for read_CSV, and then I say for I in sequence along file list. Sequence along file list is the numbers 1 through 10. It's a sequence along a length 10 character vector. Then I say here, I want to assign to data list data names I. So this is just the name, the first name for the first iteration of this data list vector. This is me subsetting by names. I could do this a number of other ways. I want to assign to this element the result of read CSV, paste on the directory name to the actual file name. I have to do this paste on it because I need to tell R to go browse into my example data directory, stick onto that each file name. This loop then is going to assemble a example data /CSV1, example data /CSV2, so on and so forth, and read each of those files individually, okay? So basically I've read in these files, and let's say you're in a situation where every one of the files you read in has the same data structure. Maybe you read in 100 files, they all have the same columns. Well, if they're all a list like that, where each element is a data frame, you probably want to stick them together into one data frame. So a convenient way to do that is the bind_rows function. So bind rows is a dplyr function, and if you give it a list and all of those list elements are data frames that have the same column names, it will take them all and scrunch them together like rbind does into one big data frame. I do that here, I take a look, and it's taken my 10 CSV files, compressed them into a single 10,000 row data frame, okay? This is again an example of an operation. It's a little bit complicated, but if you want to use a loop to load lots of files, you can steal my code and do it and modify it for your own purposes. Again, I try not to teach anything I don't use on a day-to-day basis. Okay. I think this is the last one. One of the last things I want to talk about today is another type of loop called while loops. So this is a little bit lesser used in R. Normally you'd use a while loop. I mean, as a statistical example would be, you could have a while loop that runs or like a Markov chain Monte Carlo model until it converges on parameter estimates. Not the only common example I can think of for a while loop in R, other than the example I'm going to show you in a second. So what the while loop does is rather than iterating over some vector, it's just a loop that will go forever until a logical statement returns a false. So as long as some logical statement is a true, it just keeps going and going and going and going. Okay. An example might be, let's see how many times we got to flip a coin to get 4 heads. Okay. So here I say, take the number of heads as 0 and the number of flips as 0. This is me pre-allocating values for this that are going to change. I'm going to add numbers to these. Okay. Basically, every time I flip a coin, if it's heads, I want to add 1 to this. But whether it's heads or tails, I want to add 1 to the number of flips. I'm counting. So I say, while the number of heads is less than 4, do this loop. So as long as this statement, as long as this num heads element here is less than 4, it's just going to run this loop forever. Okay. Then what I'm going to do is I'm going to flip a coin. I'm going to say coin flip is equal to a random draw from a binomial distribution, 1 draw of size 1 with a probability of 0.5. That's a coin flip. You get 1 random draw. It comes out as either a 0 or a 1. Okay. I'm going to say a heads is a 1. So if my coin flip is equal to 1, take the number of heads and add 1 to it. So I just take num heads, add 1 to it, and replace the original num heads. This increments it by 1. Okay? And then I don't use an else statement after this. I just say no matter what, so it runs this only if this is true. If it's false, it still keeps going and does this. Either way, it's going to run this next line. This line says take the number of flips, add 1 to it. It runs this loop until it's done flipping coins. It's only done when the number of heads is 4. The result here is when I first ran this operation, I had to flip my coin 11 times to get 4 heads. It's a simple simulation. Okay. If you're a stats nerd, this number of flips follows a negative binomial distribution. Fun facts. Okay. So this is a toy example of a while loop, but it's actually kind of a useful one. I mean, you might think of some situation where you want to simulate out something like this, counts to something. When do you get certain random numbers like that? Or you might do something like you've got some kind of operation like maybe you pull down Twitter data until you run out of, so if you're like downloading Twitter data, you have a limited number of times you can download data in a time period. You might just tell it to download until that number hits 0 and then stop. Saturate it. Done that before. Okay. Last thing last thing I think today is just vectorization real quick. So let's say we had a big vector of numbers. So in this case, I say I just want to add the number 1 to each element of a randomly generated vector that is 100 million numbers long. So 100 million numbers is a pretty big vector, okay? So if I wanted to add 1 to each element, I could do something very dumb. I could write a loop to do it. So what I'm doing here is this proc.time. Proc.time takes the current system time in R, okay? I assign it to for start. This allows me to start a clock in R so I can time how long it took this garbage loop to run. Okay, anyway, I'm going to pre-allocate a new vector. It's just going to be NAs for length equal to my vector. So I just created a vector of 100 million NAs. Then what I'm going to do is for position in 1 to 100 million, I want to take new vector, that position is equal to my original vector, that position plus 1. So what this means is this loop iterates 100 million times, one element at a time, adding 1 to each element. Okay? So I then figure out how long it took this to run. This took 92.43 seconds to run. Okay. A minute and a half is a really long time for my computer to be doing anything. This is very upsetting, okay? The idea that you could add 1 to a vector and have it take a minute and a half is some serious 1980s shit, okay? Right? We don't want this to be happening. This is because loops, especially badly done loops, are very slow. Okay, A better way to do this would have been to just take advantage of R's vector addition. If I say my vector length 100 million plus 1, R immediately makes plus 1 length 100 million and does this entire operation in parallel. Every one of those additions done simultaneously. I assign this to new vector. This took 0.18 seconds to do the exact same operation, okay? So this method was 1,019 times faster when these slides were generated, okay? So vector and matrix arithmetic like this is implemented using very fast optimized functions your for loop cannot compete with. Most of them are actually calculated under the hood directly, basically by your hardware. They're calling out to some C operation, some Fortran operation, or some actual underlying matrix assembly operation, probably in the case of this. Nothing you write in R manually will ever compete with that kind of speed. So whenever possible, do those operations like this rather than writing a loop. This manages to be way easier to write and 1,000 times faster, okay? The thing is, though, is that there are a lot of these vectorized functions in R to do tasks that I may demonstrate a loop with. For instance, maybe I want to get the sums of rows, of columns, the means of rows, the means of columns. So if I was working with that Swiss data set to get the means of the columns that I showed in my first example, yeah, I could run a loop that does the means, or I could just say call means Swiss, and it's going to calculate it in 100 times less time, but produce the same result. So for instance, if I've got some matrix like this is just the numbers 1 through 12, 3 rows, 4 columns, I could say row sums of a matrix, and it would just calculate the sum across this row, the sum across this row, the sum across this row, and provide the results as a vector. Writing loops sucks. Everything about this lecture is a way to show you how writing loops sucks. So whenever possible, do things like this. Don't do them with a loop. Do them with a function that does it for you. Yes, this lecture is designed to scare you away from loops because you shouldn't be writing them. Anyway, other things are like the cumulative sum, cumulative product, cumulative minimum, cumulative maximum. These will give you back vectors with cumulative quantities, running totals you might normally calculate with a loop. Okay? Position minimum and position maximum do this. For each position in a set of vectors, it finds the maximum value. So Pmax says, okay, this is position 1, this is position 1, this is position 1. Get the maximum of that position. Oh, it's 2. The max in this position is 2. The max in this position is 4, right? These are also things you might use a loop to calculate, but no, do not use a loop. Use this function that's vastly faster and probably has error checking. So there's a question in here. So with this, loops become a bit of a brute force way to do the function. Yes, loops are always the brute force option. They are the most brutish of brute force options, okay? It's not even really a hammer. It's like a crude wooden shillelagh ripped directly off a tree used to bludgeon your problems to death. Almost always there is a better way to solve a problem than a loop. Okay, but every once in a while, you will not be able to figure out a way to solve your problem with anything else. And so it is crucial to know how to use them. But you should appropriately be scared of them. If you solve all your problems with loops, your life will be much harder than if you know how to write this more efficient like code. You need to know how to use loops, but just try not to. And I'm at a point where I've been coding in R like a really long time where it is so hard for me to write loops because I just never have to write them. Every time like I think of something that's like, I could do with a loop, but it's a pain in the ass. I've been doing this for what? Oh God, like 6 years of R coding. I still find loops to be a huge pain. They suck, they're annoying. There's always some better vectorized way to do it, or at worst an apply function, which I'm gonna teach you about next week. But you need to know how them because loops underlie everything, right? The funny thing is these functions like cumulative sum and Pmax under the hood are probably a loop written in C++ because that's a language where loops are faster than anything. So it's nice to know they work with loops. Here's a question here, hypothetical example. I have a data set with 100 variables, but only 20 variables are numeric. What's the fastest way to calculate the means for those 20 variables? Dplyr mutate if is.numeric tilde mean open parenthesis period close parenthesis close parenthesis. So you do that, it will calculate the mean on every numeric variable in the data frame with a single call. Or in dplyr 1.0, it would be just summarize across is dot numeric, same tilde thing. But yeah, never do it with a loop. Okay. Okay, so the homework for this week is the part 2 of homework 5 assigned previously. So the answer key is now posted for homework 5 part 1. You can feel free to use the answer key as the basis for your part 2, which means if you didn't finish part 1 or you're not happy with the way your part 1 looks, start over using the answer key that's posted. That's great, because at least then it doesn't have any weird errors or anything in it. Go ahead. If you want to continue using your original one, absolutely go for it. Go either way. Okay. So, anybody have any questions? Yeah, thanks for bearing with me on the tough lecture. So this one is very important, but it's very difficult, and that's okay. Next week, you're going to see that R can do most of these cool things, looping over stuff without you writing an actual loop. So it'll save some, and hopefully you won't have to torture yourself with loops. I spent maybe a solid 2 years of my R coding life doing literally everything with loops. I'm really just trying to save you from that trauma. Okay. Okay. If there's no questions, I will cut out. Slack channel, email, usual on problems. We'll have lab on Monday, and like usual, we'll walk through the homework. If you don't like walking through homeworks, don't show up and do it yourself. See you folks on Monday.